Welcome, curious minds, to What Is, the channel where we unravel the mysteries of the universe, one fascinating concept at a time. Today, we're diving headfirst into a topic that surrounds us, flows through us, and keeps the world moving, often without us even realizing it. We're talking about the invisible forces that shape our skies, propel our vehicles, and even dictate how your morning coffee swirls. Today, we ask, what is fluid dynamics? At its heart, fluid dynamics sounds like the sort of phrase you'd expect to hear from a stern professor in a tweed jacket, perhaps surrounded by chalkboards filled with equations that look more like arcane symbols than numbers. And while there are certainly plenty of those equations, the concept itself is far more intuitive and frankly cooler than that image suggests. Let's break it down, shall we? First, the fluid part. When we say fluid, what comes to mind? Water, naturally. But it's not just liquids. In physics, a fluid is any substance that continually deforms or flows under an applied shear stress. So that includes liquids, yes, but also gases. And for the truly hardcore, even plasma and some plastic solids can be considered fluids under certain conditions. Basically, if it wiggles, sloshes, or rushes, it's a fluid. Air is a fluid. Smoke is a fluid. Your blood, a fluid. Even the atmosphere of Jupiter, a mighty fluid. Then there's dynamics. This is the study of motion and the forces that cause it. Think of it as the action word in our phrase. So put them together, and fluid dynamics is, quite simply, the branch of physics concerned with the movement of fluids, liquids and gases, and the forces acting on them. It's about understanding how water flows through a pipe, how air currents lift an aeroplane, or how a simple drop of rain falls. It's not just about what the fluids are, but how they behave when they're on the move, or even when they're just sitting there ready to move. It's the science of flow, torrent, calm, and chaos, all rolled into one magnificent, albeit sometimes bewildering package. And trust me, it's not just for rocket scientists and submarine designers, though they certainly do use it a lot. It's for anyone who's ever wondered why a curveball curves, or why a boat floats, or why you can't quite get all the ketchup out of the bottle. It's everywhere. Now, how did we even begin to grasp something as intricate as the movement of an invisible air or the unpredictable rush of a river? Like many great scientific endeavors, the story of fluid dynamics begins not with supercomputers, but with curiosity and a keen eye on the natural world. Our journey takes us back to the giants of ancient Greece. Think Archimedes, all the way back in the 3rd century BCE. He wasn't just shouting Eureka in the bathtub for aesthetic reasons. He was figuring out buoyancy, the principle that explains why objects float or sink. It's a foundational concept in fluid statistics, the study of fluids at rest, which is the chill, laid-back cousin of fluid dynamics. He essentially laid down the first rule book for objects interacting with liquids, proving that science can, indeed, begin in the bath. Fast forward many centuries past the fall of empires and the rise of New Thought to the Renaissance. Enter Leonardo da Vinci, not just a painter, sculptor, and inventor, but a meticulous observer of nature. He sketched swirling eddies in rivers, documented the flow of water, mused on the complexities of turbulence. His notebooks are filled with surprisingly accurate depictions of fluid motion, centuries before the mathematical tools existed to fully explain them. He was, in essence, drawing the future of fluid dynamics. Then came the giants of the scientific revolution. Isaac Newton, famous for gravity and calculus, also gave us early laws on fluid resistance and viscosity, essentially how thick or sticky a fluid is. He helped us understand why molasses flows slower than water does. The 18th century really got the ball rolling, or should I say the fluid flowing. Daniel Bernoulli, who you might know from his principle about the relationship between fluid speed and pressure, was pivotal. His work explains how an aeroplane wings generate lift and why race cars are shaped the way they are. Then there was Leonhard Euler, who gave us the first proper equations for fluid motion, laying the groundwork for mathematical analysis. But the real heavyweight contenders arrived in the 19th century. Claude Louis Navier and George Gabriel Stokes. They independently developed what are now known as the Navier-Stokes equations. These are a set of partial differential equations that describe the motion of viscous fluid substances. They are notoriously complex, incredibly difficult to solve, and one of the 7 Millennium Prize problems, with a $1 million reward for anyone who can prove their existence and smoothness under certain conditions. Basically, if you can solve them definitively for all conditions, you're not just rich, you're a legend. No pressure. The 19th and early 20th centuries also saw Osborne Reynolds doing groundbreaking work on distinguishing between laminar flow, smooth, orderly flow like water from a gently running tap, and turbulent flow, chaotic, swirling flow like a raging river. His Reynolds number is still a critical tool for engineers today. Then came the airborne revolution. The Wright brothers and the pioneers of aviation didn't have supercomputers, but they intuitively understood aerodynamics. As planes got faster and more complex, so did the need for a deeper understanding of how air behaves around them. This pushed fluid dynamics into the modern age, leading to wind tunnels, experimental data, and eventually the rise of computational fluid dynamics, or CFD. CFD, born in the mid-20th century with the advent of digital computers, revolutionized the field. Instead of building countless physical models and testing them in wind tunnels, engineers could now simulate fluid flow on a computer. This was a game changer, allowed for rapid iteration and design optimization that simply wasn't possible before. From drawing turbulent eddies, we moved to calculating them with astonishing precision. So we've defined it, and we've traced its illustrious history. But what does any of this mean for us? Why should we care about things that wiggle, slosh, and rush? The uses of fluid dynamics are so vast and varied, they underpin almost every aspect of modern life. It's truly one of those sciences that keeps the world turning, flying, and flowing. Let's start with the obvious: aerospace. Without a deep understanding of aerodynamics, airplanes just wouldn't fly. Fluid dynamics dictate wing design, engine efficiency, and even the shape of the fuselage to minimize drag and maximize lift. From the smallest drone to the largest jumbo jet, to rockets escaping Earth's atmosphere and re-entry vehicles screaming back down, it's all intricately designed using fluid dynamic principles. The very air that holds a plane up is also the medium trying to hold it back. Then move to automotive design. Car manufacturers spend millions perfecting aerodynamics of their vehicles. Why? For everything from fuel efficiency to stability at high speeds, that sleek tapered look isn't just for aesthetics, it's to cut through the air, minimize drag, and reduce turbulence. Even small improvements can save tons of fuel over a car's lifetime. Out on the water we have marine engineering. Ships, submarines, oil rigs. How do you design a hull that slices efficiently through water, or a submersible that can withstand immense pressure? Fluid dynamics. It dictates speed, stability, and even how much fuel a vessel consumes. And yes, even your meticulously designed swimming pool owes a small debt to understanding water flow and filtration. Looking up, meteorology and oceanography rely heavily on fluid dynamics. Weather prediction models are essentially massive, complex fluid dynamic simulations of the atmosphere. Understanding ocean currents, climate patterns, and the formation of hurricanes or typhoons, it all comes down to the flow of massive fluid systems on a planetary scale. It's why weathermen can't predict if you need an umbrella, even if they occasionally get it wrong. It's not easy predicting global fluid chaos. In civil engineering, it's crucial for designing everything from bridges that can withstand powerful winds without swaying like a noodle, to dams managing vast reservoirs of water, to efficient urban drainage systems that prevent cities from flooding. Even the flow of air around skyscrapers is studied to ensure pedestrian comfort and structural integrity. And it gets even more intimate. Biomedical engineering. Your heart is a pump, your blood is a fluid. Understanding blood flow, how arteries narrow, how artificial heart valves function, or how drugs are delivered through the bloodstream, it's all fluid dynamics. Even breathing involves the intricate flow of air into and out of your lungs. It's the silent hero of your cardiovascular system. Ever wondered why a golf ball has dimples, or why Olympic swimmers wear certain suits? Sports science. Those dimples aren't just for decoration, they create a thin, turbulent layer of air that actually reduces drag, allowing the ball to fly further. Swimmers and cyclists benefit from designs that minimize friction and turbulence in water or air, shaving precious milliseconds off their times. It's the hidden science behind athletic performance. And in our everyday lives, from the simple act of turning on your kitchen tap and watching water flow, to the complex mechanics of your air conditioning system, to the perfect pour of a craft beer, or how your vacuum cleaner sucks up dust, fluid dynamics is implicitly at play. So next time you're frustratingly trying to get that last bit of toothpaste out the tube, remember it's not you, it's fluid viscosity and pressure at work. So if fluid dynamics has done so much for us already, what does the future hold? It's not just about refining aircraft or predicting weather a bit better. The next frontiers are truly exciting. Computational fluid dynamics, CFD, will continue to evolve. With even more powerful supercomputers and the integration of artificial intelligence and machine learning, simulations will become unbelievably detailed and accurate. Imagine designing a new medical device and simulating its interaction with the human body's fluids down to the cellular level, or predicting the exact aerodynamic stress on a space shuttle during re entry with unprecedented precision. We're moving towards digital twins of complex systems, where every fluid interaction is modeled precisely. Sustainability and renewable energy are huge areas. Fluid dynamics is key to optimizing wind turbine blade designs for maximum energy capture, developing more efficient hydroelectric power plants, and even exploring novel approaches to wave energy conservation. It will also play a role in carbon capture technologies, understanding how gases flow and mix to separate carbon dioxide from industrial emissions. Biomimicry is another fascinating direction. Nature has had millions of years to optimize fluid interaction. Researchers are studying how fish swim, how birds fly, and how plants transport water to inspire new designs for everything, from underwater vehicles to microfluidic devices. Imagine a submarine designed to move like a whale, or a flying machine that glides like an albatross. In space exploration, fluid dynamics will be essential for designing advanced propulsion systems. Understanding the fluidic behavior of non Earth atmospheres for future planetary probes, and even managing fluids in zero gravity environments on long duration space missions. And back on Earth, in healthcare, we're looking at personalized medicine with microfluidic devices that can diagnose diseases from a tiny blood sample. We're talking about incredibly precise drug delivery systems and even growing artificial organs that mimic the complex fluid dynamics of natural tissues. Perhaps the biggest frontier, and frankly the one that keeps many scientists up at night, is still turbulence. Despite centuries of study and powerful computers, the full understanding and prediction of turbulence remains one of the grand challenges in physics. It's the chaotic, swirling, unpredictable aspect of fluid motion that makes the weather so hard to perfectly predict and limits the efficiency of many machines. Unlocking its secrets could revolutionize everything from aircraft design to industrial processes. From Archimedes in his bathtub to supercomputers simulating galactic winds, fluid dynamics has been a cornerstone of scientific progress. It's a field that seamlessly blends abstract mathematics with tangible, real world applications, profoundly impacting how we live, travel, and understand our universe. So the next time you see a cloud drift across the sky, feel the wind on your face, or watch a river flow, remember the intricate dance of forces and motions orchestrated by the principles of fluid dynamics. It's not just a scientific discipline, it's the invisible hand that shapes our world and continues to push the boundaries of what is possible. And that, my curious friends, is fluid dynamics. If you enjoyed this journey into the world of flow, be sure to hit that like button and subscribe to What Is for more deep dives into science and discovery, and ring that notification bell so you never miss an episode. What other mysteries would you want us to unravel? Let us know in the comments below. Thanks for watching, and see you next time. What if I told you that every single thing you are, your bones, your blood, your Beatles t-shirt, that questionable taco you had at 2 a.m. last Tuesday, all of it is made of the exact same element, and not just you. Every living thing on this planet, every tree, every bacteria, every dog that's ever eaten something it shouldn't have. That element is carbon, and without it, life as we know it simply wouldn't exist. But here's the weird part. Carbon is everywhere. It's in the pencil you're probably fidgeting with right now. It's in the air you breathe, well, some of it. It's in diamonds, which your partner hopefully has somewhere in a jewelry box. It's also in something like 85 million tons per year of carbon dioxide emissions that we're adding to the atmosphere. So today, we're going to answer the question that sounds like it should be simple, but gets surprisingly philosophical. What is carbon, and why is it the building block of life? This is What Is, and let's get into it. The concept, first things first. Carbon is an element. It's number 6 on the periodic table, which means it has 6 protons in its nucleus. The name comes from the Latin word carbo, which means charcoal. And honestly, that's kind of adorable. The ancient Romans named an element after burnt wood. They had no idea they'd be naming the foundation of all biology. Carbon is what we call a non-metal. It's not shiny like gold, it's not magnetic like iron. It's relatively lightweight, and at room temperature, it's mostly solid. Well, depending on the form. More on that later. But here's the thing that makes carbon special. The thing that makes it the rock star of the periodic table. Carbon atoms have a remarkable ability to bond with other carbon atoms. And I mean really bond with them. They can form long chains, branch structures, rings, you name it. Carbon can essentially build its own playground. Think of it like this. Remember when you were a kid and you had those little magnetic building toys? Where you could connect sticks in all sorts of configurations? Carbon is kind of like that. Except instead of magnetic sticks, you've got chemical bonds. And instead of toy structures, you've got molecules that make up every living thing on Earth. This property, the ability to form complex varied structures, is called catenation. And carbon is the undisputed champion of catenation. Other elements can do it too, but none do it as well as carbon. It's like carbon went to chemistry school and got a PhD in being incredibly versatile. The chemistry explained. Now I know what some of you might be thinking. Okay, cool. Carbon bonds with itself, but why does that matter? Why does that make it the building block of life? Great question. Let's break it down. Life is complicated. Like really complicated. Your body alone contains trillions of cells, each one running thousands of chemical reactions every second. And those reactions need molecules that can store information, catalyze processes, provide structure, and do a million other jobs. Carbon is the only element that can do all of this. Here's why. Each carbon atom has 4 electrons in its outer shell, and it wants 8. That's the magic number for stability. So carbon can form 4 chemical bonds with other atoms. 4. That's a lot of possibilities. It's like having 4 hands, each one able to hold hands with a different friend. But it's not just about the number of bonds, it's about the types of bonds carbon can form. Carbon can form single bonds, 1 shared pair of electrons, double bonds, 2 shared pairs, and even triple bonds, 3 shared pairs. It's like having the ability to give a handshake, a high five, or a full bear hug depending on the situation. And carbon doesn't just bond with itself. It can bond with hydrogen, oxygen, nitrogen, sulfur, phosphorus, basically almost everything on the periodic table. It's the social butterfly of chemistry. It gets along with everyone. This versatility means carbon can form millions of different compounds. And when I say millions, I'm not exaggerating. As of right now, chemists have identified or synthesized over 10 million carbon compounds. 10 million. And that's probably just the beginning. There are probably millions more that we haven't discovered yet. For contrast, the next most versatile element is probably silicon, which can form maybe a few thousand compounds. Not bad silicon, but you're no carbon. Where carbon comes from? Cosmic origin. So where does all this carbon come from? How did it get here? Well, this is where things get spacey, literally. Carbon wasn't always here. In fact, in the early universe, right after the Big Bang, there was only hydrogen and helium. That's it. Those were the only elements floating around for the first few 100 million years. Everything else, carbon, oxygen, iron, all of it, had to be created. And how do you create new elements? You need stars. Inside stars, nuclear fusion is happening constantly. Stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on. It's like a cosmic alchemy project that's been running for billions of years. But here's the crazy part. The carbon in your body, yes, the carbon making up your DNA, your proteins, your cells, that carbon was actually created inside a star that exploded billions of years ago. Your carbon atoms are literally billions of years old. You are made of star stuff. Carl Sagan was right when he said we are made of star stuff. Actually, there's a fun saying in astronomy. We are all made of star debris. And it's not poetry, it's chemistry. Every carbon atom in your body was forged in the heart of a dying star through a process called triple alpha process, where 3 helium nuclei fuse together to form carbon. So the next time someone calls you stardust, they're being scientifically accurate. Carbon and the origin of life. Now let's talk about how all this carbon actually became life. This is where things get really interesting. And honestly, a little mysterious. We don't know exactly how life started on Earth. There are several theories, and they all have their supporters and critics. But what we do know is that carbon was absolutely essential to whatever happened. The leading theories suggest that life probably started with simple carbon-based molecules in something like a primordial soup, a mixture of chemicals in Earth's early oceans that got zapped by lightning, or heated by volcanic activity, or irradiated by the early sun. Over millions of years, these simple molecules started doing something remarkable. They started making copies of themselves. This is the key step. Whatever first happened, it involved molecules that could store information and replicate. And those molecules were almost certainly carbon-based. Why? Because carbon is the best at storing information. The DNA in your cells is essentially a code written in carbon. The double helix structure, 2 strands of sugar and phosphate connected by base pairs, it's all carbon-based chemistry. The sequence of bases, adenine, guanine, cytosine, and thymine, carries all the information needed to build and maintain a human being. That's 3 billion base pairs, in every cell. It's the most efficient information storage system we know of. And it's not just DNA, RNA, proteins, lipids, carbohydrates, the 4 major classes of biological molecules. They're all built on carbon backbones. Carbon is the skeleton that holds biology together. Think about it this way. If you wanted to build a building, you'd use steel or concrete. If you wanted to build a computer, you'd use silicon. If you want to build life, you use carbon. It's the only element with the right properties. Alright, before we keep going, I wanted to take a quick break. If you're finding this content helpful, if you're learning something new, make sure you hit that subscribe button and notification bell. We do videos like this every day, explaining the science behind the world around us, so don't miss out. Alright, let's get back to it. The carbon cycle, essential for life continuing. But here's the thing, carbon isn't just important for the origin of life, it's critical for life continuing to exist. And that brings us to the carbon cycle. The carbon cycle is the process by which carbon moves between the atmosphere, the ocean, the land, and living things. It's like a giant recycling system that's been running for billions of years. Let's break it down simply. Plants take in carbon dioxide from the atmosphere through photosynthesis. They use that carbon to build their structures, stems, leaves, roots, everything. When plants die, or when animals eat plants, that carbon gets transferred. It might get released back into the atmosphere through respiration, or it might get buried underground. Over millions of years, buried carbon can become fossil fuels, coal, oil, natural gas. That's carbon that was pulled out of the atmosphere a long time ago and stored underground. And then, over the last couple of centuries, we've been digging it up and burning it, releasing all that stored carbon back into the atmosphere. The ocean also plays a huge role. It absorbs carbon dioxide from the atmosphere, and marine organisms use carbon to build their shells. When those organisms die, their carbon-rich shells sink to the ocean floor, eventually becoming rock. Over geological time, this rock can be pushed up above sea level, exposing it to the air, where it weathers and releases carbon back into the atmosphere. This whole cycle is incredibly important because it regulates the amount of carbon in the atmosphere. And that matters because carbon dioxide is a greenhouse gas. It traps heat in the atmosphere. Too much carbon dioxide and the planet warms up. Too little, and the planet might become too cold for life as we know it. For most of Earth's history, the carbon cycle has been roughly balanced. Carbon goes into the atmosphere, carbon comes out. But right now, because of human activities, we're adding way more carbon to the atmosphere than the cycle can handle. That's the whole climate change thing you've probably heard about. We'll get to that in a bit. But first, let's talk about something more fun. The different forms carbon can take. Different allotropes of carbon. Carbon is kind of like a chameleon. It can look completely different depending on how its atoms are arranged. These different forms are called allotropes, and they're pretty wild. Let's start with the most famous, diamond. Diamond is pure carbon, with each carbon atom bonded to 4 other carbon atoms in a tetrahedral structure. This makes diamond incredibly hard. In fact, it's the hardest natural substance known to science. Diamond is so hard that it can only be scratched by another diamond. But here's a fun fact that always blows people's minds. Diamond and graphite, the stuff in pencils, are both made of nothing but carbon. The only difference is how the carbon atoms are arranged. In graphite, carbon atoms are arranged in layers that can slide past each other. That's why graphite is so soft and flaky. It's basically like a deck of cards, where you can easily shuffle the cards apart. Those layers are what make graphite a great lubricant, and also what makes it perfect for writing. The layers rub off easily onto paper. So next time you write with a pencil, remember, you're using the same element that's in engagement rings, just arranged slightly differently. Then there's graphene, which is basically a single layer of carbon atoms arranged in a hexagonal pattern. It's only 1 atom thick, but it's incredibly strong, about 200 times stronger than steel. Scientists love graphene because it has amazing properties. It's an excellent conductor of electricity, it's nearly transparent, and it's incredibly strong. The people who discovered graphene won the Nobel Prize in 2010. And let's not forget fullerenes, also known as buckyballs. These are carbon atoms arranged in spherical or cylindrical shapes. The most famous is C60, which looks like a soccer ball made of carbon. Fullerenes are named after Buckminster Fuller, the architect who designed geodesic domes that look just like C60 molecules. There are also things like carbon nanotubes, essentially rolled up sheets of graphene, and amorphous carbon, which is carbon without a crystalline structure. Basically, carbon can be anything from the hardest substance on Earth to one of the softest, depending on how you arrange it. It's like carbon is the most versatile actor in the chemistry world, playing any role it wants. Carbon in the modern world, fossil fuels, and climate. So now let's talk about the elephant in the room: carbon and climate change. As I mentioned earlier, carbon that was buried underground for millions of years in the form of coal, oil, and natural gas is now being extracted and burned for energy. When we burn these fossil fuels, the carbon combines with oxygen to form carbon dioxide, which goes into the atmosphere. And here's the problem: that carbon was originally taken out of the atmosphere over millions of years. By burning it all in a few centuries, we're putting it back much faster than the carbon cycle can handle. The result is increasing concentrations of carbon dioxide in the atmosphere, which traps heat and causes the planet to warm. This is why carbon dioxide is often called a greenhouse gas. Just like the glass in a greenhouse traps heat, carbon dioxide traps heat in the atmosphere. And as we add more carbon dioxide, the Earth is getting warmer. Now, the climate has changed naturally many times throughout Earth's history. But what's happening now is different. It's happening much faster than natural climate changes, and it's driven by human activities. The overwhelming consensus among climate scientists is that this is real, it's caused by us, and it's going to have significant impacts. But here's the thing: carbon isn't the enemy. Carbon itself isn't bad. In fact, we're made of it. The issue is the form of carbon we're adding to the atmosphere, carbon dioxide, and the rate at which we're adding it. Carbon dioxide in the atmosphere is like a blanket around the Earth. A little bit of it is a good thing. It keeps the planet warm enough for life. Too much, and the blanket gets too thick, and we overheat. The good news is that we have the technology and the knowledge to fix this. We can transition to cleaner energy sources. We can improve energy efficiency. We can protect forests that absorb carbon dioxide. And we can develop new technologies to capture carbon from the atmosphere. The challenge is doing it fast enough. But that's a topic for another video. Carbon beyond fossil fuels, organic chemistry, materials. Before we wrap up, let's talk about some of the other amazing things carbon does for us. Carbon is the basis of organic chemistry, the branch of chemistry that studies carbon compounds. Organic chemistry is literally the chemistry of life. Every medicine you've ever taken, every plastic product you've ever used, every piece of clothing you've ever worn, they're all based on carbon. Pharmaceutical companies are basically carbon architects. They design molecules with specific carbon arrangements to interact with your body's chemistry in precise ways. It's incredibly complex and incredibly important. And carbon is revolutionizing materials science. We've already talked about graphene and carbon nanotubes. There's also carbon fiber, incredibly strong and light, used in everything from race cars to airplanes to sports equipment. And there's activated carbon, which is used in water filters and air purifiers because it can absorb all kinds of impurities. Even something as simple as carbon black, which is basically just very fine carbon particles, is used in millions of products. It's what makes car tires black. It's used in inks and paints. It's in rubber products of all kinds. Carbon is so useful that there's an entire field of chemistry dedicated to it. And every year, chemists discover new carbon compounds with new properties. Who knows what we'll come up with next? Why carbon is the building block. So let's bring it all together. Why is carbon the building block of life? Because it's versatile. Carbon can form millions of different compounds, each with different properties. That gives life an almost unlimited palette to work with, because it can form complex structures. Carbon chains, rings and branches can store information, provide structural support, and facilitate chemical reactions. That's exactly what life needs, because it's stable enough to hold information, but reactive enough to participate in chemistry. Carbon strikes the perfect balance, because it bonds with so many other elements. Hydrogen, oxygen, nitrogen, sulfur, phosphorus, carbon can work with them all. That's how we get the diversity of biological molecules. And because it's abundant. Carbon is the fourth most abundant element in the universe by mass. It's the 15th most abundant in the Earth's crust. Wherever there's life, carbon is there. Life chose carbon for a reason, and that reason is that carbon is the best tool for the job. And that's carbon. What an element, right? If you enjoyed this video, make sure you subscribe to What Is. We make content like this every single day, taking complex topics and breaking them down into something you can actually understand and enjoy. Hit that subscribe button and turn on notifications so you don't miss out. Also, if there's a topic you've always wondered about, something you've wanted to understand but never quite got, leave it in the comments below. We read everything, and your ideas might inspire our next video. Thanks for watching. And now for our bonus fact. Bonus fact. Here's a wild one. Your body replaces most of its carbon atoms about once a year. Through eating, drinking, and breathing, you're constantly taking in new carbon and losing old carbon. So in a very real sense, the carbon that made up you a year ago is gone. You're literally not the same atoms you were last year. But here's the trippy part. The carbon itself is old. As I mentioned earlier, that carbon was forged in stars billions of years ago. So while your body is constantly cycling through carbon atoms, those specific carbon atoms have been around since before the Earth existed. You're a temporary arrangement of eternal matter. That's carbon for you. The element that makes up everything you are has been around since the dawn of the universe, and will be around long after we're gone. Thanks for watching What Is. See you next time. Imagine you're sitting in a cockpit. You're strapped into a seat that costs more than a suburban home, surrounded by glass and glowing buttons. Behind you, two massive engines are screaming with the force of 50,000 horses. And outside the window, the air is rubbing against the skin of your aircraft so hard that the metal is beginning to glow a dull, angry red. You're traveling at 3 times the speed of sound. At this velocity, the friction of the atmosphere is heating the nose of your plane to 600 degrees Fahrenheit. In any other era of human history, your plane would be melting. It would be warping like a plastic spoon in a microwave. But you're not worried. Why? Because you're wrapped in a cocoon of the most miraculous, stubborn and expensive metal humanity has ever pulled from the dirt. Welcome to the world of titanium. Today, on What Is, we're diving into the space metal. We're looking at where it came from, why the Cold War was basically one big fight over it, and why your hip replacement has more in common with a fighter jet than you think. To understand titanium, we first have to understand the problem with everything else. For the longest time, if you wanted to build something big and strong, you used iron or steel. Steel is great, it's reliable, it's the old faithful of the periodic table. But steel has 2 major flaws. It's heavy and it hates water. It rusts if you even look at it funny. Then there's aluminum. Aluminum is the light, breezy cousin. It's fantastic for soda cans and foil, and it revolutionized early flight because it's a fraction of the weight of steel. But aluminum has a melting point problem. It gets soft when it gets hot. If you try to fly a plane made of aluminum at Mach 3, you're basically flying a giant silver stick of butter. Enter titanium. Element number 22. Titanium is the overachiever of the transition metals. It has the strength of steel, but is 45% lighter. It is twice as strong as aluminum, but only 60% heavier. It's the Goldilocks metal. It's just right. And to top it off, it is virtually immune to corrosion. You can drop a block of titanium into the ocean, come back in 100 years, and it'll look exactly the same. Humans knew titanium existed for over a century before we had any clue what to do with it. It all started in 1791. A British clergyman and amateur geologist named William Gregor was poking around in a stream in Cornwall. He found some curious black sand that looked like gunpowder. He realized there was a new metal inside it, but he couldn't quite isolate it. He called it monaconite, not the catchiest name. A few years later, a German chemist named Martin Heinrich Klaproth found the same stuff in an ore called rutile. Klaproth didn't know about Gregor's discovery at first, but he knew he'd found something powerful. He chose a name that set a very high bar. He named it after the Titans of Greek mythology, the giant immortal precursors to the gods. The name was perfect, but the metal was a nightmare. You see, titanium is a bit of a social butterfly. It loves oxygen, it loves nitrogen, it loves carbon. Whenever you try to heat it up to melt it down, it immediately sucks those elements out of the air and becomes brittle and useless. For over 100 years, titanium was just a laboratory curiosity, a forbidden fruit of metallurgy. It wasn't until the 1930s and 40s that a guy named William Kroll figured out a way to produce it in bulk by using magnesium and a lot of heat in a vacuum. This became the Kroll process. It was expensive, slow, and dangerous. But it worked. And it happened just in time for the world to go completely insane. Before we get to the spy planes and the secret shell companies, we have to look at what aerospace looked like before titanium took over. In the early days of flight, we were basically flying kites with lawnmower engines. We used wood, wire, and canvas. Even in World War II, some of the most successful planes, like the de Havilland Mosquito, were made largely of plywood. But as jet engines appeared, wood burned and aluminum started to reach its limits. The faster a plane goes, the more air it has to push out of the way. This creates friction, which creates heat. By the time we reached the 1950s, engineers were hitting the thermal barrier. If they wanted to go faster, they needed a metal that wouldn't lose its integrity at 500 degrees. They needed the titan. The first real titanium era began in the 1950s, but it wasn't easy. The United States military realized that if they wanted to build the next generation of jets, they needed this stuff by the ton. The problem? Most of the world's high-quality titanium ore was located in the Soviet Union. This leads us to one of the most hilarious and ironic stories in the history of the Cold War, the birth of the SR-71 Blackbird. The SR-71 was designed to be the ultimate spy plane. It flew at 85,000 feet and traveled at Mach 3.2. At those speeds, the skin of the plane would reach 600 degrees Fahrenheit. Aluminum would have melted. Steel would have been too heavy to get off the ground. The plane had to be made of titanium, but the US didn't have enough. So the CIA set up a series of fake front companies all over the world. These shell companies approached the Soviet Union and said, "Hey, we're looking to buy some titanium for, making pizza ovens and medical equipment. Definitely not for top secret spy planes that will fly over your country." The Soviets, needing the hard currency, sold it to them. The USSR literally provided the raw materials for the very planes the US used to spy on them. If that's not a comedic peak of international espionage, I don't know what is. But working with that titanium was a saga in itself. Engineers at Lockheed's Skunk Works found out that titanium was incredibly temperamental. If you used a cadmium-plated wrench to tighten a bolt, the bolt would later fail because of cadmium embrittlement. If you used a certain type of ink to mark the metal would crack along the lines of the ink. They had to reinvent every tool and process just to handle this diva of a metal. The result, however, was a masterpiece. The SR-71 didn't just use titanium for its strength, it used it for its weirdness. The plane actually leaked fuel on the runway because the panels were designed to fit loosely. Once it hit Mach 3, the heat caused the titanium to expand, sealing the gaps and making the plane airtight. It was a machine that only worked when it was screaming hot. Since the days of the Blackbird, titanium has become the backbone of modern aerospace. If you've flown on a Boeing 787 Dreamliner or an Airbus A350 recently, you are flying in a titanium-heavy machine. In modern jet engines, titanium is used for the fan blades. These blades have to spin at thousands of revolutions per minute while being blasted by hot air and occasionally swallowing a stray bird. Titanium can handle that stress without deforming. And it's not just about heat, it's about weight. In the airline industry, weight is literally money. Every pound you shave off the airframe is a pound more of fuel or cargo you can carry. By replacing steel parts with titanium, manufacturers save thousands of gallons of jet fuel over the life of the plane. Before we get into the weird, non-flying ways we use titanium today, and there are some very strange ones, we need to talk about you. If you're enjoying this deep dive into the elements that build our world, make sure to hit that subscribe button for the What Is channel. We're on a mission to explain the complex things in life with a bit of history and a lot of facts. Give this video a thumbs up if you think the CIA buying titanium for pizza ovens is the ultimate power move. Now let's get back to the metal that's probably inside your body right now. So Aerospace is the big client, taking up about 80% of all titanium produced. But what about the other 20%? Well, if you've ever had a knee replacement, a hip replacement, or a dental implant, congratulations, you are part cyborg, and your spare parts are made of titanium. Titanium has a property called biocompatibility. Most metals, when put inside the human body, cause the immune system to freak out. They corrode, they cause infections, or the body tries to wall them off. Titanium is different. Because it immediately forms a thin, stable oxide layer on its surface, the human body basically thinks it's part of the furniture. In fact, there's a process called osseointegration. This is a fancy way of saying that human bone will actually grow into and bond with titanium. Your bone cells see titanium and think, oh neat, a new neighbor, and they move in. This is why titanium is the gold standard for medical implants. It's strong enough to support your weight and friendly enough to live in your leg for 40 years. Then there's the sports world. In the 1990s, titanium became the ultimate flex for rich hobbyists. Titanium golf clubs, titanium bicycle frames, titanium tennis rackets. Because titanium is so springy and light, it allowed golfers to have much larger club heads without making the club too heavy to swing. This created a larger sweet spot, which basically meant people who were bad at golf could suddenly hit the ball further. It was a revolution in the dad sport industry. But here's a fact that usually blows people's minds. The most common use of titanium isn't in planes, or hips, or golf clubs. It's in your bathroom and your kitchen. Specifically, titanium dioxide. When titanium reacts with oxygen, it creates a white powder that is incredibly bright and opaque. This is the whitest white humanity has ever found. It's used as a pigment in almost everything. Your white house paint? Titanium. The white M on an M and M? Titanium. The sunscreen you put on your nose? Titanium. Toothpaste? Yup, titanium. We are literally surrounded by this element, even if we don't see it in its metallic form. It's the silent white ghost inside our consumer products. So where is titanium going next? The biggest hurdle for titanium has always been the price. It's not actually rare. It's the 9th most abundant element in the Earth's crust. It's everywhere. The problem is that it's trapped in ore, and it's a nightmare to refine. The Kroll process we mentioned earlier involves giant vats of molten magnesium and argon gas, and it takes a massive amount of electricity. This is why titanium costs about $20 to $30 a pound, while steel costs about 30 cents. But the future is looking shiny. Researchers are working on new ways to refine titanium using electrolysis, which could slash the cost. If we can make titanium as cheap as aluminum, the world changes. Imagine cars that never rust and weigh half as much. Imagine skyscrapers that are virtually earthquake-proof because they are so light and strong. And then there's the ultimate frontier, deep space. If we ever want to build a permanent base on Mars or the Moon, we can't keep dragging steel up there. It's too heavy. Titanium is the perfect candidate for space construction. Even better, we found that the lunar soil, the regolith, is actually quite rich in titanium. One day we might not be sending titanium into space. We might be mining it on the Moon to build the ships that take us to the stars. We've also started 3D printing with titanium powder. This is a game changer for aerospace. Instead of taking a giant block of titanium and carving away 90% of it to make a part, which is incredibly wasteful, we can now grow complex parts layer by layer. This allows engineers to create shapes that are impossible to machine, making engines even more efficient. Titanium is the metal of the future because it's the metal that doesn't quit. It handles the heat, it ignores the salt of the sea, and it plays nice with our biology. It took us 200 years to figure out how to tame it, but now that we have, there's no going back. From the black sands of Cornwall to the edge of the atmosphere and the joints in our own bodies, titanium is the silent titan holding our modern world together. If you found this story of the space metal fascinating, don't forget to like and share this video. It helps the channel grow and allows us to keep bringing you these deep dives. Check out our science playlist above for more What Is videos on every element, from gold to carbon. And now, as promised, for staying until the end, here is your bonus fact that we didn't mention anywhere else in the script. You know how some metals have a smell? Like when you hold a bunch of copper pennies or a steel railing and your hands get that metallic scent. Titanium is one of the few metals that is truly 100% odorless. That metal smell you get from iron or copper isn't actually the metal itself. It's a chemical reaction between the metal and the oils on your skin. But titanium is so chemically inert and resistant to reacting with your skin oils that it produces no scent whatsoever. If you were to walk into a room filled with 1,000 tons of pure titanium, it would have no smell at all. It is the literal phantom of the elements. Thanks for watching What Is, and we'll see you in the next one. Welcome back to What Is, where we take the most complex concepts in the universe and try and explain them before your coffee gets cold. Although today's topic is so big, you might want to grab a refill, and maybe a snack. Today we're talking about the most important book ever written. It's a book that's inside you right now. In fact, it is you. It's also in your dog, the banana that you had for breakfast, and that weird mold growing in the back of your fridge. We're talking about DNA. But what is it really? Is it a blueprint, a code, a twisted ladder, or is it just nature's way of making sure you have your mother's nose and your father's questionable sense of direction? First things first, the name. Deoxyribonucleic acid. It sounds like something a wizard would scream while casting a hex, but it's actually a very literal description of what the molecule is made of. Deoxyribo refers to the type of sugar it uses, deoxyribose. Nucleic tells us that it lives in the nucleus of your cell, and acid? Well, it's an acid. If you were to take the DNA from just one of your cells and stretch it out, it would be about 2 meters long. That doesn't sound like much until you realize that you have 37 trillion cells. If you unravel all your DNA and laid it end to end, it would stretch from the Earth to Pluto and back. Twice. Yet it fits inside a space so small you can't see it without a high-powered microscope. Nature is the world champion of packing. Take that, IKEA. Structurally, DNA is a double helix. Imagine a ladder that someone took both ends of and twisted like a piece of licorice. The sides of the ladder are made up of sugar and phosphate, but the rungs, the parts that you would step on, are where the magic happens. These rungs are made up of 4 chemical bases: adenine, thymine, cytosine, and guanine. Or as scientists call them because they're busy people, A, T, C, and G. These 4 letters are the entire alphabet of life. Every living thing on this planet is written in a language that only uses 4 letters. Imagine trying to write War and Peace using only the letters A, B, C, and D. Nature did one better. It wrote the instructions for the blue whale, a redwood tree, and Jeff Goldblum, using nothing but A, T, C, and G. The secret is the order. The sequence of these bases is a code. It's a biological software. It tells your cells how to build proteins, and proteins do everything. They build your muscles, they digest your food, they carry oxygen in your blood. If your body is a construction site, DNA is the architect's master plan, and the proteins are the actual bricks and the guys laying them. But how did we find this out? It's not like we were born knowing we had microscopic licorice ladders in our blood. The discovery of DNA is one of the greatest detective stories in history, filled with brilliant minds, massive egos, and a healthy dose of academic saltiness. For a long time, Scientists knew that traits were passed down. They knew that if you bred two fast horses, you'd probably get a fast horse, but they didn't know how. Most people thought proteins carried the genetic information because proteins were complex. DNA was seen as the boring molecule, too simple to do anything important. Enter Frederick Nietzsche in 1869. He wasn't looking for the secret of life, he was looking at white blood cells in pus. Yes, pus, from discarded surgical bandages. He isolated a substance he called nuclein. He didn't know what it did, but he knew it was different. Fast forward to the early 20th century. We start realizing that chromosomes have something to do with heredity. Then in the 1940s, Oswald Avery and his team proved that DNA, not protein, was the transforming principle. Essentially, they showed that if you changed a cell's DNA, you changed the cell. This sparked a literal race. It was the 1950s version of the space race, but instead of the moon, everyone was heading for the center of the cell. On one side, you had Linus Pauling in California, the greatest chemist of his age. On the other, you had a ragtag duo at Cambridge, a fast-talking American named James Watson, and a brilliant eccentric Brit named Francis Crick. But there was a third player, often overlooked in the history books, Rosalind Franklin. Franklin was a master of X-ray crystallography. She spent countless hours bombarding DNA fibers with X-rays to see how they scattered. She captured an image known as Photo 51. It is arguably the most important photo ever taken. It showed a distinct X shape, which was the smoking gun evidence that DNA was a helix. Now here's where the drama starts. Morris Wilkins, Franklin's colleague who didn't exactly get along with her, showed Photo 51 to Watson without her permission. Watson saw it, and in his own words, his mouth fell open and his pulse began to race. He realized the X meant a double helix. Watson and Crick rushed to build a model. They used cardboard cutouts of bases and pieces of metal. On February 28, 1953, they walked into the Eagle pub in Cambridge and famously announced they had found the secret of life. They won the Nobel Prize. Rosalind Franklin unfortunately passed away from cancer at age 37 before the prize was awarded. Because the Nobel isn't given posthumously, her contribution was largely ignored for decades. So let's take a second to say, thank you, Rosalind. We couldn't have done it without you. Since 1953, our understanding hasn't just grown, it's exploded. In the 1990s, we started the Human Genome Project. It was an international effort to map every single letter in the human spirit. It took about 13 years and cost about $3 billion. Today, we can sequence a human genome in a few hours for less than it costs for a high-end smartphone. What has this given us? For starters, forensic science. Before DNA profiling, if a criminal didn't leave a fingerprint or get spotted by a witness, they were basically home free. Now a single skin cell or a drop of saliva can link a suspect to a crime scene with staggering accuracy. It's also revolutionized medicine. We're moving into an era of personalized medicine. Instead of giving everyone with the same disease the same pill, doctors can look at your specific DNA to see which treatments will work for you and which ones will just give you weird side effects. Then there's CRISPR. If DNA is the book, CRISPR is the find and replace tool. It's a piece of technology that allows scientists to go into a living organism and precisely snip out a piece of DNA and replace it with something else. We're talking about the potential to cure genetic diseases like sickle cell anemia or cystic fibrosis. We've already used it to create mosquitoes that can't carry malaria and crops that can grow in droughts. It's the closest thing to a magic wand we've ever invented. But with great power comes, well, you know that quote. And there's also the ethical headaches to consider. If we can edit DNA to cure diseases, can we edit it to make someone taller, stronger, smarter? Where do we draw the line between healing and designing? These aren't science fiction questions anymore. They're Tuesday questions. So where are we going? What does the future of DNA look like? Well, it's time to buckle up because this is where it gets weird. First, DNA data storage. Humans are producing data at an unsustainable rate. Our hard drives and cloud servers are made of silicon and metal, and they don't last forever. But DNA? DNA is the most stable, compact information storage system in the known universe. Scientists have already successfully encoded the entirety of Wikipedia, several books, and a short film into DNA. A single gram of DNA can store 215 petabytes of data. That's 215,000 terabytes. You could fit the entire history of human knowledge into a shoebox full of DNA. And unlike a USB stick, which will be obsolete in a few years, we'll always have hardware that can read DNA, as long as we're still human, that is. Then there's de-extinction. You've seen Jurassic Park. You know how it ends, usually with a lot of screaming. But scientists are legitimately working on bringing back the woolly mammoth by splicing mammoth DNA into the genome of the Asian elephant. They aren't trying to make a theme park, they're trying to restore ecosystems. Mammoths help maintain the grasslands of the Arctic, which keeps the permafrost frozen. Bringing them back could actually help fighting climate change. Finally, we're looking at synthetic biology. We aren't just reading or editing DNA anymore, we're writing it from scratch. We're creating synthetic life forms, bacteria that are programmed to eat plastic in the ocean or produce carbon-neutral jet fuel. We're moving from being the students of life to being the authors. It's a lot to take in. From Friedrich Nietzsche's bandages to the digital biological future, DNA has gone from a mystery to a tool. It's the thread that connects us to every creature that's ever lived. You share 99.9% of your DNA with the person sitting next to you. You share 98% with a chimpanzee. You even share about 60% with a banana. So the next time you feel like you don't belong, just remember you're part of a 4 billion-year-old story written in a language that the entire planet speaks. You're a walking, talking, thinking collection of instructions that the universe spent eons perfecting. And that's pretty incredible. If you enjoyed this deep dive into the code of life, make sure to hit that like button. It helps our channel's algorithmic DNA thrive. Don't forget to subscribe to What Is so you never miss a video. What should we explore next? Dark matter? The history of the internet? The mystery of why we still use fax machines? Let us know in the comments. Thanks for watching and stay curious. See you in the next one. Imagine you're standing on a tall building, looking down at the street below. You drop a marble. It falls. You drop a bowling ball. It falls at exactly the same speed. Not faster, not slower. Exactly the same. Now here's the crazy part. This exact same phenomenon happens on the moon. If you drop that marble and bowling ball on the moon, with no air resistance, they'd hit the lunar surface at the exact same instant. Even though the moon is 238,900 miles away. This isn't magic. This isn't coincidence. This is one of the most powerful ideas humanity has ever discovered, a law of physics. And today, we're going to unpack what that actually means. Welcome to What Is, and today we're answering the question, what is a law of physics? So what is a law of physics? Before we dive in, let's get one thing straight. When physicists talk about laws, they don't mean rules that someone invented and enforcing upon the universe. These aren't like speed limits or no smoking ordinances. These are discoveries. Observations about how the universe actually behaves, consistently, everywhere, all the time. Think about that for a second. Every time you throw a ball, every time light bends through a window, every time your phone's accelerometer detects motion, something like 40 different physical laws are quietly doing their jobs. But here's where it gets really interesting. These laws aren't just true, they're predictive. They allow us to build machines that fly, predict where planets will be decades from now, and, perhaps most impressively, understand things we've never actually seen. Let's start from the beginning. Defining the concept. A law of physics is essentially a concise mathematical or verbal description of how the universe behaves under specific conditions. It describes a relationship that holds true every single time, everywhere in the observable universe. Sounds simple, right? Well, buckle up, because the simplicity is deceptive. The key word here is every single time. That's what makes a law different from a theory or a hypothesis. A hypothesis is an educated guess. A theory is a well-substantiated explanation. But a law? Oh, a law is something different. Here's a helpful analogy. Think of laws of physics like the rules of a game. Except the game is reality, and the rules were never written by anyone. They were discovered. When Newton watched that apple fall, he didn't create gravity. He discovered that there's a relationship between mass, distance, and the force pulling objects together. The relationship was always there. Newton just had the brilliance to see the pattern. That's what physics laws do. They identify patterns so fundamental that they govern everything from the smallest subatomic particles to the largest galaxies. The big players. Let me introduce you to some of the most famous laws of physics. These are the rock stars of the physics world. Names you've probably heard, even if you don't remember what they actually describe. Newton's 3 laws of motion. These are the foundation of classical physics. First law, an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. This is sometimes called the law of inertia. Second law, force equals mass times acceleration, or F equals ma. This is the equation that lets engineers calculate exactly how much thrust a rocket needs to launch. Third law, for every action, there is an equal and opposite reaction. This is why you feel recoil when firing a gun. The bullet goes forward, the gun pushes back with the same force. It's also how rockets work. Exhaust goes one way, the rocket goes the other. The law of universal gravitation. This is Newton's big one. Every object in the universe attracts every other object with a force that depends on their masses and the distance between them. That apple that fell on Newton's head? It was attracted to the Earth. But here's the mind-blowing part. The apple was also attracting the Earth. The force is just so tiny when one object is an apple and the other is an entire planet that we don't notice the Earth's movement. Conservation laws. These are absolutely crucial. The laws of conservation of energy, momentum, and mass state that certain quantities cannot be created or destroyed. They can only be transferred or transformed. Energy conservation is particularly wild. It means the energy in your body right now is the same energy that's been circulating through the universe since the Big Bang. You're literally carrying around 13.8 billion years of stored starlight in your cells. Thermodynamics. These laws describe heat, energy, and work. The first law is essentially conservation of energy applied to thermal systems. The second law, which is where things get fascinating, states that entropy always increases in an isolated system. Entropy is a measure of disorder or randomness. This law explains why time appears to flow in one direction, why you can't unscramble an egg, and why perpetual motion machines are impossible. Einstein's laws. Albert Einstein gave us 2 especially important ones. The theory of special relativity gave us the famous E equals mc squared, showing that mass and energy are interchangeable. It also told us that nothing can travel faster than light, a speed limit built into the very structure of space-time. General relativity redefined gravity entirely, showing that massive objects don't just attract other objects, they actually bend the fabric of space-time itself. What we perceive as gravity is actually objects following curved paths through warped space. If you're finding this fascinating, you're not alone. But here's the thing. Channels like this one exist because of people like you. If you're enjoying this video, hit that subscribe button. Join the What Is community, because there's a whole universe of questions left to answer. We explore science questions like these every Monday, and other topics every day of the week. Don't miss out. Now let's get back to the physics, how laws are created. Now here's where people often get confused. How do we know these laws are real? Who decides what's a law and what's just a good guess? Great questions. The process is beautifully rigorous. It starts with observation. Someone notices something interesting. Maybe it's a pattern in how planets move, or how light behaves when passing through water. Then comes the hypothesis. A scientist proposes a possible explanation, usually in the form of a mathematical relationship. Here's the critical part. The hypothesis gets tested. A lot. Different scientists, in different places, with different equipment, all trying to find a flaw in the idea. If the hypothesis survives enough rigorous testing, if it consistently and accurately predicts outcomes, it earns the prestigious title of law. But here's the catch that many people don't realize. No law is considered absolutely permanent. Scientific laws are always provisional. They're the best explanation we have, given our current understanding and technology. Case in point, Newton's laws are incredibly accurate for everyday situations, dropping balls, driving cars, launching satellites. But when you get to extremely high speeds approaching the speed of light, Newton's laws break down. Einstein's relativity takes over. And when you get to the quantum scale, the world of atoms and subatomic particles, even relativity isn't enough. We need quantum mechanics. Does this mean Newton's laws are wrong? Not really. They're right for the situations they describe. They're wrong only in the sense that they don't tell the complete story. They're like a map that's perfect for driving across a city, but useless for navigating on the moon. Physics is cumulative. New laws don't usually overthrow old laws. They extend them, or show where their domain of validity ends. This is actually one of the most beautiful aspects of physics. Each generation stands on the shoulders of the previous one, building more comprehensive understanding. Misconceptions. Let me address some common misconceptions about physics laws, because these can really trip people up. Misconception 1. It's just a theory. People often use theory loosely, meaning just a guess. But in science, a theory is as solid as it gets. A law and a theory are different things, not levels of certainty, but different types of descriptions. Laws describe what happens. Theories explain why it happens. Evolution is a theory. Gravity is a theory, both Newtonian and Einsteinian. That doesn't mean scientists are just guessing. It means these are extremely well substantiated explanatory frameworks. Misconception 2. Laws are absolute. As we just discussed, no. Laws describe relationships that hold under specific conditions. When conditions change significantly, very high speeds, very small scales, very strong gravitational fields, our laws may need revision or replacement. Misconception 3. Physics laws are invented. This is a philosophical debate, but the prevailing view among physicists is that laws are discovered, not invented. The universe behaves in certain ways. Our job is to figure out those ways. Math is the language we use to describe them, not the rules themselves. Misconception 4. Laws of physics are opinions. Some people try to dismiss scientific findings by calling them just opinions. But physics laws aren't opinions. They're rigorously tested descriptions of observable reality. If you think they're wrong, go ahead. Build better equipment, run better experiments, and publish your findings. That's exactly how science is supposed to work. Why this matters. Here's why all of this matters so much. Physics laws are the foundation of everything. Every piece of technology you've ever used, every building that stood up, every medical imaging scan, every satellite in orbit, all of it exists because we understand these laws well enough to work with them. But there's something deeper too. These laws connect us to the universe in a profound way. When you understand that you're made of atoms that formed in stellar cores and scattered across the galaxy, that understanding comes from physics. When you know that the light from distant galaxies left its source millions of years ago, That knowledge comes from physics. There's something almost spiritual about it, not in a religious sense, but in the sense of feeling connected to something vast and ancient and structured. These laws are humanity's greatest achievements. They're abstract descriptions that let us predict and control the physical world in ways that would seem like magic to anyone from just a few hundred years ago. The limits of knowledge. So we've established what physics laws are and how powerful they can be. But let's be honest about the limitations too. We don't have all the answers. There are still fundamental questions that physics hasn't solved. What is dark matter? We can't see it, but we can observe its gravitational effects on galaxies. Something is out there, making up about 27% of the universe. We have no idea what it actually is. What is dark energy? This is even stranger. The universe is expanding at an accelerating rate, and some form of energy filling all of space, is driving that expansion. We call it dark energy, but that's really just a name for we have no idea what this is. The measurement problem in quantum mechanics is deeply puzzling. At the quantum level, particles don't have definite positions until they're observed. This is deeply weird, and physicists still debate what it means. These aren't failures, they're frontiers. They're the boundaries of human knowledge, where new laws might be discovered in your lifetime. That's genuinely exciting. Every major law of physics was discovered because someone looked at the unknown and said, I want to understand this. Philosophical implications. Now let's get a little philosophical. Don't worry, we'll keep it accessible. The existence of consistent physical laws raises some fascinating questions. Why is the universe orderly rather than chaotic? Why can we discover these laws at all? Why is the universe comprehensible? Some physicists are what we call Platonists. They believe these laws exist independent of the universe, as abstract mathematical truths that the universe happens to follow. Others take a more pragmatic view. The laws are useful descriptions that work, and that's all we need to know. Either way, the fact that we can discover these laws, that our brains evolved on the African savanna to hunt and gather, can somehow comprehend the fundamental nature of reality, that's pretty remarkable. Some people find this frightening or dispiriting, that we're just governed by physical laws. But I think it's beautiful. There's something wonderful about being a collection of atoms that's evolved to the point where it can understand the very forces that created it. We are the universe understanding itself. How cool is that? Before we wrap up with our bonus fact, I want to ask you something directly. What questions do you have about physics? What concepts have always confused you? What have you heard about but never fully understood? Drop your questions in the comments below. This channel exists to answer your questions, so let's hear what you want to know. If you want more content like this, detailed explanations, fascinating facts, and the occasional deep dive into the mysteries of the universe, make sure you're subscribed. Hit the bell icon too, so you never miss a new video. Now let's end with something special. Bonus fact. Here's your bonus fact for today. The most precise physical law ever measured is something called the electromagnetic moment. Scientists have calculated this value to an accuracy of about 1 part in a trillion. That's like measuring the distance between New York and Los Angeles to within the width of a human hair. This level of precision was achieved over decades of careful experimentation, and it represents one of the most accurate agreements between theory and experiment in all of science. But here's what's really interesting. This extreme precision almost didn't happen. The original calculations suggested there might be a slight discrepancy from theoretical predictions. This anomaly prompted decades of additional research, improved experimental techniques, and eventually led to even more precise confirmations of our best theories. Sometimes what looks like a problem turns out to be an opportunity for deeper understanding. That's the spirit of physics. That's the spirit of science. So there you have it. A law of physics is a concise description of how the universe behaves, a relationship that holds true everywhere, every time, under specific conditions. These laws aren't rules imposed on reality. They're discoveries about the fundamental nature of existence. They connect us to the cosmos in profound ways, and they make modern civilization possible. Thanks for watching What Is. I'll see you in the next one. Imagine you're standing on a hill, looking up at a night sky full of twinkling lights. You might think you're seeing a whole bunch of tiny flashlights glued to a black canvas. But what's actually between those lights? Spoiler, it's not just darkness. It's the most mind-boggling, ginormous, and surprisingly empty real estate in the universe. So what is space? Grab a cup of coffee, or a spacesuit, if you fancy, and let's dive into the cosmic equivalent of an empty attic, but one that stretches for billions of light years. Defining the void. When scientists talk about space, they usually mean the region beyond Earth's atmosphere, where the air we breathe gives way to a near-perfect vacuum. But calling it empty is a bit like calling your junk drawer clean. It's technically true, but there's a lot of hidden stuff going on. First, let's clear up a common myth. Space isn't completely empty. It's filled with a thin soup of particles, radiation, and fields. Think of it as the universe's version of a low-fat broth, so thin that a cubic centimeter might contain only a handful of atoms, but still enough to keep physicists up at night. One of the first formal definitions came from the Fédération Aéronautique Internationale, FAI. They drew the Kármán line at 100 kilometers, about 62 miles, above Earth's surface. Below that, you need a plane. Above that, you're officially an astronaut. It's a neat line, but nature doesn't really care about our paperwork. The atmosphere gradually thins out, blending into what we call the exosphere, and finally into interplanetary space. A brief history of the void. Humans have been staring at the sky for millennia, but the idea of space as a physical place is surprisingly modern. Ancient Greeks, like Aristotle, believed the heavens were a series of concentric crystalline spheres, no empty void between them. It wasn't until the 17th century, with telescopes peering at the moon and planets, that thinkers like Galileo and later Newton started to imagine a space that could exist on its own, independent of Earth. In the 20th century, the term outer space entered the lexicon, especially after the launch of Sputnik in 1957. Suddenly, the void became a frontier, a place you could actually visit if you had the right hardware. The word space itself comes from the Latin spatium, meaning distance or room. Fitting, because that's exactly what it provides. Room for planets, stars, galaxies, and of course, your imagination. The space right above us. Let's zoom in on the layer just above our heads. The atmosphere gradually thins, but it doesn't just stop at the Kármán line. The thermosphere, for instance, stretches from about 80 kilometers to 600 kilometers. That's where the International Space Station, ISS, orbits. Even there, the air is so thin that a human would suffocate in seconds, but it's thick enough to create drag, slowing the station down ever so slightly. Above that lies the exosphere, which fades into the solar wind, a constant stream of charged particles blown out by the sun. This region is the first taste of true interplanetary space. It's also where we start to see the cosmic microwave background, CMB, the afterglow of the Big Bang, peeking through the leftover radiation. If you've ever heard the phrase, space is a vacuum, you're not wrong, but it's a vacuum with a twist. It's not a perfect void. There are photons, light particles, neutrinos, and even occasional atoms wandering around. It's the universe's way of saying, I may be mostly empty, but I'm never completely lonely. Interplanetary space. The sun's backyard. When we talk about interplanetary space, we mean the region between the planets of our solar system. It's dominated by the sun's influence, the solar wind, magnetic fields, and a constant rain of charged particles. The solar wind travels at speeds of about 400 kilometers per second. That's roughly 1 million miles per hour, creating a bubble called the heliosphere that shields the inner planets from galactic cosmic rays. Now here's a fun fact that might make you chuckle. The solar wind is essentially the sun's exhale, and it smells, if you could smell it, like, well, astronomers think it smells a bit like burnt toast, because it contains trace amounts of carbon and oxygen. Not that you'd want to get close enough to take a whiff. Interplanetary space also hosts the asteroid belt, the Kuiper belt, and countless comets. These icy and rocky relics are leftovers from the solar system's formation, floating in a region that's mostly empty, but dotted with ancient building blocks. It's like a cosmic yard sale, where the items are millions of miles apart, and the price is measured in astronomical units. If you're enjoying this cosmic ride, hit the like button, and don't forget to subscribe for more out-of-this-world content. Let's keep exploring together. Interstellar space, beyond the sun's reach. Once you cross the heliopause, the boundary where the solar wind slows down and gets compressed, you step into interstellar space. This is the realm between stars, the true void that makes up most of the volume of our galaxy, the Milky Way. The interstellar medium, ISM, is a tenuous mix of gas and dust, with an average density of about 1 atom per cubic centimeter. To put that in perspective, a decent vacuum chamber on Earth can achieve a density that's lower than that. So in many ways, the best laboratory vacuum on Earth is actually dirtier than the average interstellar space. The ISM isn't uniform. It's a tapestry of hot, warm, and cold regions. The hot, ionized gas, heated by supernova explosions, can reach millions of degrees, while the cold molecular clouds are the birthing grounds for new stars. It's a place where the leftovers of dead stars mix with the ingredients for future suns, a cosmic recycling center that never closes. Intergalactic space, the vast between. Step even further out, past the edges of the Milky Way and other galaxies, and you enter intergalactic space. This is where galaxies themselves are like isolated islands in an ocean of almost nothing. The density here is even lower, roughly 1 atom per cubic meter, which is about as empty as any environment we can observe. Yet intergalactic space isn't completely deserted. It contains the intracluster medium, ICM, a hot X-ray emitting plasma that fills galaxy clusters. It also holds dark matter, an invisible scaffold that gravitationally binds galaxies together. Without dark matter, our Milky Way would be a far less cohesive place, and we'd probably have drifted apart eons ago. And then there's the cosmic web, a giant network of filaments made of dark matter and gas, connecting galaxies across billions of light years. It's the universe's way of playing connect the dots, but the dots are galaxies, and the lines are invisible to the naked eye. The observable universe. How far can we see? Now let's talk about the ultimate horizon, the observable universe. Light has traveled for about 13.8 billion years since the Big Bang, and that gives us a sphere of about 46 billion light years in radius. Within that sphere lie roughly 200 billion galaxies, each containing billions of stars. But here's the kicker. The universe is expanding. The distance between us and faraway galaxies is increasing, meaning that the light we see today has been stretched or redshifted into longer wavelengths. The most distant objects we can observe, the so-called first galaxies, appear to us as they were just a few 100 million years after the Big Bang. It's like looking at a baby picture of the cosmos. What lies beyond the observable universe? Honestly, we don't know. It could be more of the same. Infinite galaxies, stars and planets. Or it could be something entirely beyond our comprehension. The universe might be infinite, or it might be curved in a shape we can't visualize. Either way, the answer is humbling. Dark matter and dark energy, the invisible players. If space were a cake, the atoms we're made of would be the frosting. a tiny, tasty layer on top. The rest of the cake is dark matter and dark energy, two mysterious ingredients that make up about 95% of the universe. Dark matter doesn't emit, absorb, or reflect light, making it essentially invisible. We infer its presence from the gravitational effects it has on visible matter, like the way galaxies spin faster than they should based on their visible mass. It's as if there's an invisible scaffolding holding everything together. Dark energy, on the other hand, is the mysterious force driving the accelerated expansion of the universe. Think of it as the universe's own dark side, a sort of anti-gravity that pushes galaxies apart, making the cosmic web stretch ever faster. Neither of these phenomena can be directly seen, but they shape the large-scale structure of space in profound ways. Why space matters, even if you're grounded. Now you might ask, why should any of this matter to someone sitting on a couch, scrolling through cat videos? The answer is surprisingly practical. Space research has given us GPS, weather satellites, memory foam, water purification, and even the smartphone in your pocket. But beyond technology, understanding space feeds our curiosity. It reminds us that we're part of something larger, something that stretches far beyond our planet. It inspires artists, philosophers, and dreamers. It challenges us to ask the biggest questions. Where did we come from? Are we alone? What's the ultimate fate of the universe? And let's be honest, space is just plain cool. The sheer scale, the mind-bending physics, the beauty of a nebula. It's a source of wonder that transcends borders and cultures. It's a shared human heritage that belongs to everyone, even if most of us will never get to float among the stars. So what is space? It's the near vacuum that fills the cosmos, the stage on which galaxies dance, the medium through which light travels, and the mystery that continues to puzzle scientists and dreamers alike. From the thin air above Earth to the vast intergalactic voids, space is both empty and full, empty of matter, but rich with phenomena, history, and possibility. As we continue to explore, we'll undoubtedly discover new layers, new questions, and maybe even new answers. The journey is far from over. It's just beginning. And the best part? You're already part of it. Every time you look up at the night sky, you're peering into the very space we've just talked about. If you enjoyed this deep dive into the cosmos, please hit the subscribe button, ring the bell, leave a comment with your favorite space fact, and share this video with friends who love a good cosmic mystery. Your support helps us keep exploring the universe, one video at a time. Bonus fact. And now, here's a bonus fact that didn't make it into the main script. Floating in the Milky Way, about 25,000 light-years from Earth, there's a giant cloud of alcohol. It's called Sagittarius B2, and it contains enough ethanol to fill billions of trillions of pints. So if you ever needed proof that the universe has a sense of humor, there you have it. Cheers to space. What if I told you that you could steal an hour from your boss, slip it into your pocket, and use it to finally finish that Netflix series you've been pretending to watch? Sounds like a heist movie, right? Well, the truth is, we're all already time thieves, just not the glamorous kind with masks and getaway cars. We're constantly borrowing, lending, losing, and sometimes even pretending we have more of it than we actually do. So today, on What Is, we're going to unravel the slippery, stretchy, mind-bending concept that governs our lives, our jokes, and our existential crises. Time. We're about to take a quantum leap through physics, philosophy, psychology, and a few laugh-out-loud moments that prove even the universe has a sense of humor. The everyday experience of time. Let's start where we all live, the mundane. You wake up, glance at your phone, and see that it's 7:03 a.m. You sigh, hit snooze, and somehow convince yourself that those 9 extra minutes are a gift from the time fairy. In reality, you're just delaying the inevitable march of the second hand, a march that, according to your alarm clock, is indifferent to your desire for more sleep. This daily tug-of-war between intention and illusion is a perfect microcosm of how we experience time. As a flowing river, we can sometimes paddle against it, but never truly stop. Measuring time. From sundials to atomic clocks. Humanity's obsession with quantifying that river led to some pretty inventive tools. Ancient Egyptians tracked the sun's shadow with obelisks, turning sunlight into a rudimentary clock. The Greeks later refined this with water clocks, or clepsydra, which measured time by the steady drip of liquid, because nothing says precise like watching water slowly escape a pot. Fast forward to the Middle Ages, and mechanical clocks began to appear in town squares, their gargoyles keeping watch over the ticking hours like stone-cold bureaucrats. Today we've traded those gritty contraptions for atomic clocks, which measure time based on the consistent frequency of cesium-133 atoms transitioning between energy states. If you could hear the tick of an atomic clock, it would sound like a hyperactive metronome set to 9,192,631,770 beats per second, so precise that it would lose less than a second over 100 million years. Imagine trying to be late for a meeting when your watch is that accurate. The only excuse left would be, I got caught in a quantum fluctuation. Physics, time as a dimension. Now let's dive into the deep end, where physicists treat time not as a flowing river, but as a dimension, much like length, width, and height. In Einstein's theory of relativity, space and time are woven together into a four-dimensional fabric called space-time. This means that your movement through space affects how you experience time. The faster you move, the slower time passes for you relative to someone standing still, a phenomenon known as time dilation. If you hopped on a spaceship traveling at 90% the speed of light and took a round trip to a nearby star, you might return to find that only a few years have aged you, while decades have passed on Earth. It's the ultimate, I was only gone for a quick coffee excuse, except the coffee break lasts a lifetime. And if that wasn't mind-bending enough, general relativity tells us that gravity also warps time. Clocks run slower near massive objects, like a black hole, so if you ever find yourself orbiting one, your Instagram selfies would be seriously out of sync with everyone else's feed. The arrow of time. Why we remember the past, not the future. But why does time feel like it only moves forward? Why can't we remember tomorrow's lottery numbers? Physicists call this the arrow of time, and it's largely tied to the concept of entropy, a measure of disorder. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. In plain English, things get messier unless you put energy into keeping them tidy. Think of a freshly made bed. Left alone, it will inevitably become rumpled as sheets shift, pillows slide, and perhaps a mischievous cat decides to nap in the middle. The disordered state, rumpled bed, is far more probable than the neat one, so the system naturally drifts toward higher entropy. This statistical tendency gives time its direction. We perceive the past as more ordered and the future as more chaotic. In a universe where entropy were decreasing, we'd have memories of the future and anticipate the past. Imagine showing up to work yesterday because you remembered tomorrow's meeting. Philosophical takes, presentism versus eternalism. Physics gives us the equations, but philosophy asks, what does it mean? Two major camps dominate the debate. Presentists argue that only the present moment is real. The past is gone, the future hasn't happened yet. Eternalists, on the other hand, see past, present, and future as equally real points in the space-time block, like frames in a film reel. To an eternalist, your birth, your graduation, and your retirement all exist simultaneously. We just happen to be conscious of the slice we're currently inhabiting. If you've ever felt déjà vu, the eerie sense that you've lived a moment before, you might flirt with the idea that time is more like a looping ribbon than a straight line. Some philosophers even entertain the notion of growing block universes, where the past and present are fixed, but the future is still being generated. It's like a cosmic Netflix series that's still being written, with us as both audience and unwitting scriptwriters. Psychology: how our brains warp time. Even if physics and philosophy agree on the nature of time, our brains have a hilarious habit of distorting it. Ever noticed how a boring lecture seems to last an eternity, while a fun night out flies by in what feels like minutes? This isn't just your imagination, it's a well-documented psychological effect. Our perception of time depends on attention, emotion, and memory load. When you're engaged and stimulated, your brain packs more information into each moment, making it feel longer in retrospect. Conversely, when you're bored, fewer novel stimuli are processed, and time seems to drag. Stress and fear can also stretch time. Think of the classic "time slows down during a car accident" sensation. Your brain shifts into high gear processing mode, capturing every detail, which later gets replayed in slow motion memory. On the flip side, enjoyable activities cause time to fly because we're not monitoring the clock. We're immersed in the flow state. Psychologist Mihaly Csikszentmihalyi described this as being in the zone, where self-consciousness fades and the sense of time dissolves. So next time you lose track of hours while gaming, you can thank your brain for giving you a complimentary vacation from chronometry. Cultural time, social constructs, and humor. Time isn't just a universal constant, it's also a cultural construct that shapes our jokes, rituals, and even our procrastination habits. Consider the concept of island time in many tropical locales, where schedules are more suggestive than binding. Arriving fashionably late isn't rude, it's expected. In contrast, German punctuality is legendary. Being 5 minutes late can be seen as a personal affront, akin to showing up to a dinner party in pajamas. These cultural differences give rise to comedy gold. Imagine a Swiss watchmaker trying to teach a laid-back surf instructor about precision timing. You see, the second hand moves exactly. While the instructor shrugs, "Yeah man, the wave will come when it comes." The clash of temporality becomes a source of laughter, reminding us that while physics may treat time as immutable, human societies love to negotiate its meaning. Time travel mishaps. Let's take a quick detour into the realm of sci-fi humor, because nothing highlights our relationship with time like the classic time travel paradox. Picture this: you build a time machine in your garage, hop inside, and go back to tell your younger self not to invest in that questionable cryptocurrency. You succeed, but in doing so, you erase the very motivation that led you to build the machine in the first place. Poof, you disappear, leaving only a confused younger you, wondering why there's a half-eaten sandwich on the workbench and a lingering smell of ozone. Or consider the bootstrap paradox, where you give Beethoven a copy of his own symphonies, which he then publishes, becoming famous, except the symphonies never had an original creator. It's a cosmic version of the chicken and egg problem, wrapped in a bow of bureaucratic paperwork. Please fill out Form T7 for temporal anomaly clearance. These thought experiments aren't just fodder for nerdy debates. They reveal how deeply ingrained our causal intuition is, and how delightfully wrong it can be when we mess with the timeline. If you're finding this journey through time as fascinating as a cat watching a laser pointer, smash that like button, subscribe to the channel, and ring the notification bell so you never miss an episode of What Is. Your support helps us keep digging into the weird, wonderful, and downright hilarious mysteries of the universe. And hey, drop a comment below with your favorite time-related joke, or a moment when time felt totally wonky for you. We love hearing your stories. The quantum quirk. Time at the smallest scales. Now let's zoom down to the quantum realm, where things get even stranger. At scales smaller than an atom, particles don't have definite positions or times. They exist in probabilities described by wave functions. Some interpretations of quantum mechanics suggest that time might not be fundamental at all. It could emerge from more basic quantum entanglements. In other words, what we experience as the flow of time could be a side effect of how quantum states correlate with each other. Think of it like a massive multiplayer online game. The underlying code doesn't have a built-in clock. Instead, the perception of time arises from the order in which events are processed and displayed to players. If quantum gravity theories like loop quantum gravity or string theory are correct, the smooth spacetime we see at large scales might be a mosaic of discrete, quantized chunks, like a pixelated image that looks continuous until you zoom in really close. In that picture, time would be less a river and more a series of tick-tock frames, each one a tiny update of the universe's state. Time and technology, from mechanical watches to smartphones. Our relationship with time has also been transformed by technology. The invention of the mechanical clock in the 14th century paved the way for regimented work schedules, ushering in the Industrial Revolution's factory whistles. Fast forward to the 20th century, and quartz watches brought unprecedented accuracy to the masses, making it possible to synchronize everything from train departures to TV broadcasts. Today, our smartphones sync with atomic clocks via the internet, giving us access to Universal Coordinated Time, UTC, with a tap. We can set reminders, alarms, and countdowns for everything, from meditation sessions to pizza deliveries. Yet despite this precision, we still find ourselves perpetually busy, a paradox that sociologists call time poverty. We have more tools to measure time than ever, but we often feel we have less of it to spend on what truly matters. Perhaps the real challenge isn't measuring time better, but learning how to allocate it wisely, something no app can fully solve. The future of time, speculations and possibilities. Looking ahead, scientists are exploring whether time could be manipulated or even reversed under extreme conditions. Some theoretical models propose closed time-like curves, paths in space-time that loop back on themselves, allowing for genuine backward time travel. While these solutions require exotic matter with negative energy density, think of it as the universe's equivalent of anti-gravity fuel, they remain mathematically permissible in general relativity. If we ever managed to harness such phenomena, the implications would be staggering. Historians could witness events firsthand, criminals could erase their misdeeds, and we could finally answer the age-old question: did the chicken really come before the egg? Of course, with great power comes great responsibility, and likely a whole new set of paradoxes that would keep philosophers busy for another millennium. Why time matters. So what is time? It's a dimension woven into the fabric of the cosmos, a statistical arrow driven by entropy, a philosophical puzzle about what's real, a psychological construct shaped by our attention and emotions, a cultural tool that societies mold to fit their rhythms, and a technological benchmark that keeps our modern world ticking. It's both utterly objective and strangely subjective, reliable enough to launch satellites, yet malleable enough to stretch during a kiss or shrink during a dentist's drill. In the end, time is the stage on which the drama of existence unfolds. It gives our lives structure, provides the canvas for memory and imagination, and admittedly, offers endless material for comedians who love to riff on how we're perpetually late, early, or just plain confused about when lunch is supposed to be. If you enjoyed this deep dive into the nature of time, please hit the like button, subscribe to What Is, and turn on notifications so you're first in line for our next exploration. Share this video with anyone who's ever wondered why Monday feels longer than Friday, or who just loves a good mind-bending fact. And don't forget to leave a comment below. What's your personal take on time? Is it a friend, a foe, or perhaps a mischievous trickster? We can't wait to hear your thoughts. Bonus fact: a single day on Venus, defined as one full rotation on its axis, lasts longer than a Venusian year, which is the time it takes Venus to orbit the Sun. In other words, on Venus, you could celebrate a birthday before you even finish celebrating a sunrise. Talk about taking your time. Thanks for watching, and remember, whether you're stretching a second or savoring an hour, time is the one thing we all share, even if we experience it a little differently. Stay curious, keep questioning, and until next time, keep asking, what is? Imagine you're standing on a beach, toes sinking into warm sand, the salty breeze tugging at your shirt, and you toss a pebble into the surf. It arcs, slows, then kisses the water with a gentle plop. Why does it fall? Why does the moon stay aloft while the pebble surrenders to the sea? The answer, dear viewer, is gravity, the invisible handshake that binds apples to earth, planets to suns, and galaxies to each other. Today on What Is, we're going to peel back the layers of this cosmic force, from the whimsical musings of ancient thinkers to the mind-bending equations of modern physics, with a sprinkle of humor to keep things from getting too, well, grounded. We're about to fall into the story of gravity. If you've ever wondered why you don't float off your couch when you binge watch your favorite show, or why astronauts appear to be in a perpetual slow-motion dance inside the International Space Station, you've already brushed shoulders with gravity's secretive personality. It's the ultimate clingy friend, always there, never asking for permission, and somehow managing to keep the entire universe from spiraling into chaos. But gravity isn't just a simple, what goes up must come down rule. It's a saga that stretches across millennia, filled with brilliant blunders, daring experiments, and a few aha moments that would make even the most stoic physicists crack a smile. So let's dust off the chalkboards, fire up the imagination, and embark on a chronological joyride through humanity's quest to answer the deceptively simple question: what is gravity? Ancient foundations. Our tale begins in the dusty courtyards of ancient Greece, where philosophers liked to ponder the nature of motion while sipping wine and debating whether the world was flat or a giant leather ball. Aristotle, the big-name thinker of the 4th century BCE, claimed that objects fell because they sought their natural place: earth toward the center, water a bit higher, air above that, and fire craving the heavens. In his view, heavier things fell faster because they were more earthy. It sounded logical, until you tried dropping a feather and a hammer side by side. Spoiler, they didn't race. The feather floated lazily while the hammer plummeted, exposing a flaw in Aristotle's earth-centric logic. Enter the Hellenistic astronomer Hipparchus, who, while mapping stars, noticed that celestial bodies didn't plummet to Earth. They clung to their orbits like cosmic ballet dancers. He hinted that something kept them aloft, though he lacked the vocabulary to call it gravity. Fast forward to the Islamic Golden Age, where scholars like al-Biruni and Ibn Sina, Avicenna, began questioning Aristotle's natural place theory. Al-Biruni, ever the meticulous measurer, attempted to calculate Earth's radius using mountain shadows, a feat that would later prove crucial for understanding gravitational acceleration. Yet even these sharp minds clung to the idea that celestial motions were governed by a different set of rules than earthly fall, a dichotomy that would persist for centuries. Medieval musings. The Middle Ages saw a blend of Aristotelian philosophy and theological thought. In the West, scholars like Thomas Aquinas fused Aristotle's physics with Christian doctrine, reinforcing the notion that objects move toward their divinely ordained places. Meanwhile, in the Islamic world, thinkers such as Al-Ghazali explored causality, suggesting that God's will could be the underlying cause of motion, a precursor to the idea of a universal force, though still couched in theological language. It wasn't until the Renaissance that the shackles of pure Aristotelianism began to loosen. Nicholas Copernicus, daring to place the sun at the center of the cosmos, indirectly challenged the idea that Earth was the unique center of natural motion. His heliocentric model set the stage for a new question: if Earth isn't special, why do objects still fall toward it? Galileo's Leaning Tower, enter Galileo Galilei, the Italian polymath with a penchant for experimentation and a flair for drama. In the early 1600s, Galileo reportedly climbed the Leaning Tower of Pisa, though historians debate whether he actually dropped objects from the top or simply rolled them down inclined planes to test Aristotle's claim about falling speeds. His ingenious solution? Use a smooth inclined plane to slow down the motion, making timing easier with the water clocks of the day. By rolling balls of different masses down the same slope, Galileo discovered that, neglecting air resistance and friction, they accelerated at the same rate. He articulated this insight in his work, Discourses and Mathematical Demonstrations Relating to Two New Sciences, stating that the distance traveled by a falling object is proportional to the square of the time elapsed. The famous d equals 1/2 gt squared law, where g is the acceleration due to gravity. Galileo's experiments didn't just refute Aristotle, they laid the groundwork for a quantitative description of gravity, transforming it from a philosophical notion into something you could measure, predict, and crucially, doubt. Galileo also turned his telescope to the heavens, observing the moons of Jupiter dancing around their parent planet. He realized that if Jupiter could hold moons in orbit, perhaps Earth could hold the moon, hinting at a universal principle linking celestial and terrestrial motion. Yet Galileo stopped short of naming the force. He described the motions mathematically, but left the why to future. As for why the planets move so, we must seek a deeper cause. Open. Kepler's elliptical whisper. While Galileo was busy with inclined planes, Johannes Kepler was poring over the meticulous planetary observations of Tycho Brahe. Kepler's 3 laws of planetary motion, published between 1609 and 1619, revealed that planets travel in elliptical orbits with the Sun at one focus, sweep out equal areas in equal times, and that the square of a planet's orbital period is proportional to the cube of its semi-major axis. These laws were descriptive gems, but they beg the question, what force makes planets follow these precise paths? Kepler himself toyed with the idea of a magnetic influence emanating from the Sun, but magnetism fell short when applied to the outer planets. Still, his laws provided the essential scaffold upon which Isaac Newton would later build his universal law of gravitation. Newton's apple and the myth. Now we arrive at the legendary moment, whether true or embellished, of Sir Isaac Newton sitting under an apple tree, watching a fruit fall, and suddenly grasping that the same force pulling the apple to Earth also governs the moon's orbit. Whether the apple actually bonked Newton on the head is debatable, but the insight is historic. In 1687, Newton published Philosophia Naturalis Principia Mathematica, commonly known as the Principia. Within its pages, he introduced 3 laws of motion, and most famously for our story, the law of universal gravitation. Every point mass attracts every other point mass, with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Mathematically, F equals G times m 1 times m2 over r squared, where F is the gravitational force, m1 and m2 are the masses, r is the distance between them, and g is the gravitational constant, a proportionality factor that Newton could not determine experimentally, but whose value we now know to be approximately 6.67430 times 10 to the minus 11 Newton meters squared per kilogram squared. Newton's brilliance lay in unifying celestial and terrestrial mechanics under a single mathematical framework. He showed that the same inverse square law that made an apple fall at 9.8 meters per second, squared on Earth's surface, also kept the moon in its orbit, causing it to fall toward Earth continuously, but with sufficient tangential velocity to perpetually miss, resulting in a stable orbit. Newton also tackled the problem of the gravitational constant indirectly through his work on the motion of the moon and the tides. By comparing the lunar orbital period with the known radius of Earth's orbit, he could infer the ratio of Earth's mass to the Sun's, laying groundwork for later measurements of g. The Principia didn't just explain why apples fall, it predicted the existence of Neptune, though its discovery came later, accounted for the precession of the equinoxes, and provided a framework that would dominate physics for over 2 centuries. Yet Newton himself was uneasy about the philosophical implications of action at a distance. How could 2 objects influence each other across empty space without any medium? He famously wrote, "I feign no hypotheses," acknowledging that while his equations worked, the underlying mechanism remained a mystery. If you're finding this journey through the ages of gravity as fascinating as a falling apple in slow motion, why not give this video a thumbs up? It helps the channel grow and lets us bring more deep dives like this one. And if you haven't already, consider subscribing. We've got a whole universe of What Is episodes waiting to explode into your feed. The constant G. Speaking of the gravitational constant G, its measurement became a holy grail for experimental physicists. The first successful laboratory determination came from Henry Cavendish in 1798, using a torsion balance, a delicate device consisting of a horizontal bar suspended from a thin wire with small lead spheres attached to its ends. Larger lead spheres were placed nearby, and their gravitational pull caused the bar to twist ever so slightly. By measuring the angle of twist and knowing the torsion constant of the wire, Cavendish could calculate the force between the masses, and consequently, G. His result, G approximately equals 6.754 times 10 to the power of minus 11, Newton meters squared per kilogram squared, was within about 1% of today's accepted value, a stunning achievement given the equipment of the 18th century. Cavendish's experiment not only quantified G, but also allowed the calculation of Earth's mass. Knowing G, the gravitational acceleration at Earth's surface, G, and Earth's radius, one can solve for m sub e equals gr squared over g. This turned gravity from a celestial curiosity into a tool for probing the very makeup of our planet. Einstein's revolution. Fast forward to the early 20th century, when Albert Einstein, working as a patent clerk in Bern, began to question the very foundations of Newtonian gravity. Newton's inverse square law worked splendidly for most everyday scenarios, but it faltered under extreme conditions, such as the orbit of Mercury, which displayed a tiny but persistent precession that Newtonian mechanics couldn't fully account for. Einstein's breakthrough came not from a new force, but from a radical reimagining of space-time itself. In 1915, he presented the general theory of relativity, encapsulated by the Einstein field equations. G mu nu plus lambda g mu nu equals 8 pi g over c to the fourth times t mu nu. Here, g mu nu represents the curvature of spacetime open parenthesis, the Einstein tensor close parenthesis. Lambda is the cosmological constant. G mu nu is the metric tensor describing the geometry of spacetime. T mu nu is the stress energy tensor encoding matter and energy. G is the gravitational constant, and c is the speed of light. In plain language, mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. Gravity, therefore, isn't a mysterious force acting at a distance. It's the manifestation of geometry. A planet orbiting a star isn't being pulled by an invisible string. It's following the straightest possible path, a geodesic, through curved spacetime created by the star's mass. Einstein's theory made several astonishing predictions that Newton's could not. The bending of light by massive bodies, observed during the 1919 solar eclipse, the gravitational redshift of light climbing out of a gravitational well, and the existence of gravitational waves, ripples in spacetime propagating at the speed of light. The 1919 eclipse expedition, led by Arthur Eddington, measured the apparent shift of star positions near the Sun's limb and found agreement with Einstein's predicted deflection of 1.75 arcseconds, catapulting him to international fame. General relativity also introduced the concept of black holes, regions where spacetime curvature becomes so extreme that not even light can escape. The Schwarzschild solution, derived shortly after Einstein's publication, described the spacetime around a spherically symmetric, non-rotating mass. Decades later, observations of X-ray binaries and the Event Horizon Telescope's image of M87 star would provide empirical support for these cosmic monsters. Yet even Einstein's masterpiece left questions unanswered. How does gravity fit with the other three fundamental forces? Electromagnetism, the strong nuclear force, and the weak nuclear force, which are all described by quantum field theories. And what about the cosmological constant lambda, which Einstein initially added to allow a static universe, later called it his biggest blunder? only to see it resurrected as a possible explanation for dark energy, driving the accelerated expansion of the universe. Quantum gravity. The ongoing quest. The marriage of gravity with quantum mechanics remains one of the greatest unsolved puzzles in physics. Quantum field theory excels at describing the other three forces through the exchange of force-carrying particles: photons for electromagnetism, gluons for the strong force, and W/Z bosons for the weak force. For gravity, the analogous hypothetical particle is the graviton, a massless spin-2 boson that would mediate gravitational interactions in a quantum framework. However, attempts to quantize gravity using the same techniques that succeeded for other forces run into severe difficulties. When you try to apply quantum field theory to the gravitational field, the resulting equations produce infinities that cannot be removed through the standard renormalization procedures. In other words, the theory predicts probabilities greater than 1 or nonsensical results at very high energies, a sign that our current approach breaks down. Enter string theory, proposed in the late 1960s and early 1970s as a way to describe particles not as point-like entities, but as tiny, vibrating strings. Remarkably, string theory naturally includes a spin-2 massless excitation that behaves like a graviton, offering a potential unified description of all forces, including gravity. The theory requires extra spatial dimensions, typically 6 or 7 compactified dimensions beyond the familiar 3, leading to a rich landscape of possible universes, often referred to as the string landscape. Another prominent contender is loop quantum gravity, LQG, which takes a different route. Instead of starting with strings, LQG quantizes spacetime itself. It envisions space as composed of discrete, finite loops woven together into a spin network. Areas and volumes become quantized, meaning there is a smallest possible unit of area and volume, a Planck scale granularity. In LQG, gravity emerges from the dynamics of these spin networks, providing a background-independent framework where spacetime is not a stage, but a participant. Both approaches have yielded insights. String theory has given us tools like holography, the ADS/CFT correspondence, suggesting a deep connection between gravity in a volume and quantum field theory on its boundary. Loop quantum gravity has produced concrete predictions for the discrete structure of spacetime that could, in principle, be probed by high-energy cosmic rays or gravitational wave observations. Yet neither theory has produced a definitive, experimentally verified prediction that distinguishes it from the others or from pure general relativity inaccessible phenomena. The search continues, with experiments like LIGO/Virgo detecting gravitational waves, satellite missions testing the equivalence principle to unprecedented precision, and tabletop experiments probing for deviations from Newton's inverse square law at sub-millimeter scales, all hunting for cracks in our current understanding that might point toward quantum gravity. Modern experiments and applications. Beyond the theoretical quest, gravity's influence permeates modern technology and cosmology. Global Positioning System, GPS, satellites must account for both special and relativistic time dilation. Clocks aboard the satellites run faster by about 38 microseconds per day due to weaker gravitational potential at altitude. Without correction, GPS positions would drift by kilometers each day. Gravitational lensing, the bending of light by massive clusters, acts as nature's telescope, allowing astronomers to glimpse distant galaxies, otherwise too faint to observe. The study of galaxy rotation curves and the gravitational dynamics of clusters led to the hypothesis of dark matter, an invisible substance that contributes roughly 27% of the universe's energy density, inferred solely from its gravitational effects. On the cosmological scale, the observed accelerated expansion of the universe, discovered via Type 1a supernovae in the late 1990s, suggests the presence of dark energy, a repulsive gravitational effect often associated with Einstein's cosmological constant lambda. Understanding whether lambda truly is a constant or a dynamical field remains a frontier of modern cosmology. Closer to home, precision measurements of G continue to challenge physicists. Recent experiments using atom interferometry, laser range measurements, and improved torsion balances have yielded values of G that differ by more than the quoted uncertainties, sparking debates about possible hidden systematic errors or even new physics. And let's not forget the playful side. Astronauts aboard the ISS experience microgravity, allowing them to perform graceful flips, drink floating water blobs, and grow crystals that reveal novel structures impossible under Earth's gravity. These demonstrations not only inspire the public, but also provide unique environments for studying fluid dynamics, combustion, and material science in ways that ground-based labs cannot replicate. Now let's swing back to the human side of gravity, the stories of the scientists who dared to question, experiment, and sometimes fail spectacularly. Take the tale of the Cavendish experiment. Henry Cavendish, notoriously shy, conducted his landmark torsion balance test in a sealed room to avoid drafts, all while barely speaking to his assistants. His meticulous notes, hidden away for decades, were only rediscovered later, revealing a man who preferred the quiet company of his apparatus to the limelight of scientific fame. Then there's the story of Arthur Eddington's 1919 eclipse expedition. Eddington, a pacifist Quaker, faced logistical nightmares, transporting fragile telescopes to the island of Principe off West Africa, battling tropical weather, and negotiating with local authorities. When the eclipse finally arrived, clouds threatened to ruin the observations, but a brief clearing allowed Eddington's team to capture the crucial plates that would later confirm Einstein's prediction. His quiet determination exemplified how curiosity can triumph over adversity. Fast forward to the modern era, where the LIGO scientific collaboration, thousands of scientists spread across the globe, spent decades building laser interferometers capable of measuring changes in distance smaller than a proton's width. When the first gravitational wave arrived on September 14, 2015, produced by the merger of two black holes over 1 billion light-years away, the signal rippled through the detectors like a cosmic heartbeat, confirming a century-old prediction and opening a new window onto the universe. These human narratives remind us that gravity, while a fundamental force of nature, is also deeply intertwined with the perseverance, creativity, and occasional quirkiness of those who seek to understand it. Before we wrap up, if you've enjoyed this epic tale of falling apples, bending space-time, and cosmic whispers, please smash that subscribe button, ring the notification bell, and share this video with anyone who looks up at the night sky and wonders what's holding it all together. Your support fuels more research-filled, fun-packed episodes and helps us keep exploring the mysteries of the universe, one what is at a time. Bonus fact. And now, for a bonus nugget that didn't fit elsewhere. Did you know that if you could somehow compress the entire mass of the observable universe into a sphere, its radius would be about 13.8 billion light-years, roughly the same as the age of the universe in light-years? This coincidence arises because the observable universe's average density is just shy of the critical density needed to halt its expansion, making the cosmos delicately balanced between eternal expansion and eventual collapse. In other words, the universe is poised on the knife edge of gravity's tug, a cosmic tightrope act that keeps us guessing about its ultimate fate. Thanks for watching. Keep questioning, keep exploring, and remember, gravity may hold us down, but curiosity lifts us higher. See you next time.